Good day, math learners. This time, I am going to discuss on the logarithmic function. So, before we proceed to our discussion, let us have this learning pocket concept map, in which, for this week's lesson, we will be dealing on the logarithmic function. Its basic concept, logarithmic equation, logarithmic inequality, and applications. But this time, we will be focusing first on the basic concept and logarithmic equation. In our previous discussion, it has been established that the exponential function f of x is equal to 2 raised to x or y is equal to 2 raised to x is increasing throughout its domain. Thus, the exponential function is a one-to-one function, and its inverse exists. Consequently, its inverse is also a function. In this illustration, we see the graphs of exponential function in the form of y is equal to 2 raised to x, and its inverse x is equal to 2 raised to y. This inverse is also known as logarithmic function, which can be written in the form of y is equal to the logarithm of x to the base 2. In the said illustration, we write the exponential function as y is equal to a raised to x, and its inverse we write it as x is equal to a raised to y. The logarithmic function is a function defined by y is equal to the logarithmic of x to the base a. If and only if x is equal to a raised to y for all positive real numbers x and a is not equal to 1. Again, it is read as y is equal to the logarithm of x to the base a. There are some applications of logarithmic functions. First, the strength of an earthquake is measured on a logarithmic scale called the Richter scale, which is based on the equation r is equal to the logarithm of I over I sub 0, where r is the Richter scale number, I is the intensity of the earthquake, and I sub 0 is the standard minimum intensity used to measure Earth's vibration. Second, a certain type of radioactive substance decomposes according to the relation of logarithm of g over g sub 0 to the base e is equal to the negative 0.04 raised to t. And for the third one, we have the height in meter above sea level, the air temperature in degrees Celsius, the atmospheric pressure C at sea level are related by the function h is equal to 30t plus 8,000 times the natural logarithm of c over p. For the conversion of exponential function into logarithmic function, since the inverse of exponential function is the logarithmic function, we have to consider this form. The logarithm of x to the base a is equal to y, means a raised to y equals x, in which a there is considered as the base and y there is considered as the exponent. Please take note, class, that a, which is the base, is greater than 0. A is not equal to 1 and y is not equal to 0. For example, the logarithm of a to the base 2 equals 3. Its exponential function is 2 raised to 3 is equal to 8. So this time, let's express the logarithmic form into exponential form. So if we have the logarithm of x to the base 2 equals y, its exponential form is 2 raised to y is equal to x. If we have the logarithm of 16 to the base 4 equals 2, its exponential form is 4 raised to 2 equals 16. If we have the logarithm of n to the base b equals x, its exponential form is b raised to x equals n. There are two types of logarithm. They are the common logarithm and the natural logarithm. When we say common logarithm, it is the logarithm to the base 10. We denote the common logarithm by omitting the subscript for the base. So, f of x is equal to the common logarithm of x, which implies that the subscript of the logarithm is 10. F of x is equal to the common logarithm x is equivalent to the function of the logarithm of x to the base 10. The function of the common logarithm x is read as f of x is equal to the common logarithm of x. The second type of the logarithm is the natural logarithm. It is the logarithm to the base e, an irrational number approximated as 2.718281828. We denote the natural logarithm by the function of the natural logarithm of x, which implies a base of e. The function of the natural logarithm x is read as f of x is equal to the natural logarithm of x. Please take note, class, that the common logarithm of a number n is equal to the sum of the characteristics n mantissa. For example, the common logarithm of 25 is equal to 1.3979400009. Its characteristics is equal to 1 and its mantissa is equal to 0.3979400009. To find the value of the common logarithm of 2 and the natural logarithm of 2, we will use the scientific calculator with this brand. For non-user of this, just discover the functions of your calculator. Here are the steps. For the common logarithm of 2, just press the keys log 2 equals, and the answer will be 0.3010299957. And for the natural logarithm of 2, just press the keys ln 2 equals, and the answer will be 0.693147186. To check your answer, convert it from logarithmic form to exponential form. Our answer earlier, we have the common logarithm of 2 is equal to 0.3010299957. So for the checking, we are going to consider 10 because the base of the common logarithm is 10 raised to 0.3010299957 equals 2. And for the natural logarithm of 2, okay, so our base is considered as e, and raised to 0.693147186, it is equal to 2. Or the value of e is considered as 2.718281828 raised to 0.693147186 is equal to 2. So this time we will be talking on the logarithm of a number and simple logarithmic equation. Take note that the concept of exponential equation is used in solving logarithm of a number, wherein the base is not equal to 10. The logarithm x of a number n to the base b is the exponent of the power to which b is raised to obtain n. In symbols, logarithm of n to the base b is equal to x. if and only if b is raised to x equals n. To evaluate the following logarithms, we have to consider this process. The given is the logarithm of 27 to the base 3. Find its value. Here are the solutions. Write the logarithm of 27 to the base 3 equals x. According to the definition of the logarithmic function, that this form can be written into this exponential form. So, we will convert the given logarithm to its exponential form, and it is 3 raised to x is equal to 27. After which, 27 can be written into exponential form, and it is equal to 3 raised to 3, because when you are going to multiply 3 by itself in 3 times, its result is 27. So our equation becomes 3 raised to x equals 3 raised to 3. Since the bases are the same, we will use the property of equality of exponential function. Therefore, x is equal to 3. Thus, the logarithm of 27 to the base 3 is equal to 3. The given is the logarithm of 0.01 to the base 10. Find its value. Here are the solutions. Write the logarithm of 0.01 to the base 10 equals x. According to the definition of the logarithmic function, that this form can be written into this exponential form. So we will convert the given logarithm to its exponential form, and it is 10 raised to x is equal to 0.01. After which, 0.01 can be written into fraction form, which is 1 over 100. So our equation becomes 10 raised to x is equal to 1 over 100. 100 can be written into its exponential form, and it is equal to 10 raised to 2, because when we multiply 10 by itself in 2 times, its result is 100. So our equation becomes 10 raised to x is equal to 1 over 10 raised to 2. According to the definition of the negative exponents, that for every 1 over a raised to 1, it is equal to a raised to negative 1. That is the law of exponents. So our equation becomes 10 raised to x is equal to 10 raised to negative 2. Since the bases are the same, we will use now the property of equality of exponential function. Therefore, x is equal to negative 2. Thus, the logarithm of 0.01 to the base 10 is equal to negative 2. For example number 3, the given is the logarithm of 5 square root of 5 to the base 5. Find its value. So, here are the solutions. Write the logarithm of 5 square root of 5 to the base 5 is equal to x. According to the definition of the logarithmic function, that this form can be written into this exponential form. So we will convert the given logarithm to its exponential form. And it is 5 raised to x is equal to 5 square root of 5. After which, square root of 5 can be written into exponential form. According to the definition of the radical expression, that for every square root of a, its exponential function is a raised to 1/2. So the square root of 5 is equal to 5 raised to 1/2. So our equation becomes 5 raised to x equals, copy 5 times the transformation of square root of 5, which is 5 raised to 1/2. So we will still simplify the right side of the equation. According to the product rule of exponents, if the bases are the same, we will copy the same base and add the exponent. So for every 5 raised to 1 and 5 raised to 1/2, okay, it is equal to 5 raised to 1 plus 1/2. So our equation becomes 5 raised to x is equal to 5 raised to 1 plus 1/2. Next, get the LCD of 1 and 1/2. So the LCD is considered as 2. Then multiply this 2 to our first number, which is 1. And the answer is 2. And copy the numerator of the second number, which is 1. So the equation becomes 5 raised to x is equal to 5 raised to 2 plus 1 over 2. So we are going to simplify this one. So we have 5 raised to x is equal to 5 raised to 2 plus 1 over 2. So 2 plus 1, the answer would be 3. And the equation becomes 5 raised to x is equal to 5 raised to 3 over 2. Since the bases are the same, so now we will be using the property of equality of the exponential function. And x is equal to 3 over 2. Thus, the logarithm of 5 square root of 5 to the base 5 is equal to 3 over 2. So this time, we will proceed to the properties of logarithms. The properties of logarithms are so useful in simplifying the process of solving logarithmic equations. These properties or laws can be derived from the laws of exponents. Remember that logarithms are merely exponents. Now, let's start looking at some properties of logarithms. We'll start off with some basic evaluation properties. The following are the properties of logarithms. So we have the first set of properties of logarithms. This is for any base b. Number 1. The logarithm of 1 to the base b is equal to 0. Example. The logarithm of 1 to the base 4 is equal to 0. The logarithm of 1 to the base 5 is equal to 0. Now, what makes this form equal to 0? It is because that the exponential form of logarithm of 1 to the base b is equal to 0 is b raised to 0 is equal to 1. According to the zero exponent, that a number is raised to 0 is equal to 1. The exponential form of logarithm of 1 to the base 4 is 4 raised to 0, and it is equal to 1. The exponential form of logarithm of 1 to the base 5 is 5 raised to 0 is equal to 1. So, that makes this logarithm of 1 to any base is equal to 0. How about the logarithm of 1 to the base 8? What is the answer? Yes, it is 0. The logarithm of 1 to the base 20, it is equal to 0. And the logarithm of 1 to the base 15 is equal to 0. For the second property of logarithm, it is for any base b, the logarithm of b to the base b is equal to 1. Example, for the logarithm of 4 to the base 4 is equal to 1. The logarithm of 5 to the base 5 is equal to 1. What makes this logarithm form is equal to 1? It is because when we transform this property to exponential form, it will become b raised to 1, and its result is b. When we transform this logarithm of 4 to the base 4 equals 1 to its exponential form, it will become 4 raised to 1 equals 4. When we transform this logarithm of 5 to the base 5 equals 1 to its exponential form, it will become 5 raised to 1 is equal to 5. And how about the logarithm of 8 to the base 8? Yes, it's still equal to 1. The logarithm of 20 to the base 20 it is still equal to 1. And for the logarithm of 15 to the base 15, it's still equal to 1. That's the second property of logarithm. Third property of logarithms, for any base b, the logarithm of 1 over b to the base b is equal to negative 1, in which b is not equal to 0. For example, the logarithm of 1/4 to the base 4, it is equal to negative 1. The logarithm of 1/5 to the base 5, it is equal to negative 1. Now, what makes this logarithmic form equal to negative 1? It is because when we transform this property to exponential form, it will become b raised to negative 1. Its result is 1 over b, which is the definition of the negative exponent. How about the logarithm of 1 over 8 to the base 8? What is the value? Yes, it's still negative 1. How about the logarithm of 1 over 20 to the base 20? Still negative 1. What is the logarithm of 1 over 15 to the base 15? Yes, it's still negative 1. And that's the third property of the logarithm. Fourth property of logarithms, for any base b, the logarithm of b raised to x to the base b is equal to x, in which b is not equal to 1 and b is greater than 0. For example, the logarithm of 3 raised to 2 to the base 3 is equal to 2. The logarithm of 5 raised to 3 to the base 5 is equal to 3. Now, what do you think is the reason for this pattern? It is because when we transform this property to exponential form, it will become b raised to x is equal to b raised to x. Now, how about the logarithm of 8 raised to 4 to the base 8? What is the value of this? Yes, it is 4. How about the logarithm of 10 raised to 5 to the base 10? Yes, it is equal to 5. How about the logarithm of 15 raised to 3 to the base 15? Yes, it is equal to 3. Fifth property of logarithms for any base b. b raised to the logarithm of x to the base b is equal to x. For example, 5 raised to the logarithm of 2 to the base 5, its result is 2. 8 raised to the logarithm of 3 to the base 8, its result is equal to 3. Now, what do you think is the reason for this pattern? It is because when you transform this property to its exponential form, it will become the logarithm of x to the base b equals the logarithm of x to the base b. How about for number 3? 2 raised to the logarithm of 4 to the base 2, the answer is 4. 4 raised to the logarithm of 3 to the base 4, the answer is 3. And 5 raised to the logarithm of 6 to the base 5, the answer is 6. That's the fifth property of the logarithm. For the second set of properties of logarithms, apply for any values of m, n, and b, for which each logarithm is defined, which is m. N is greater than 0, and b is not equal to 1, but greater than 0. So, for the product rule, the logarithm of m times n to the base b is equal to the logarithm of m to the base b plus the logarithm of n to the base b. For the quotient rule, the logarithm of m over n to the base b is equal to the logarithm of m to the base b minus the logarithm of n to the base b. And for the power rule, the logarithm of m raised to 8 to the base b is equal to a times the logarithm of m to the base b. Please consider these important notes. Expanding a logarithm means writing it as the sum, difference, or multiple of two logarithms or more. Compressing or condensing a sum or difference or multiple of two or more logarithms means writing it as a single logarithm. when we compress logarithmic expressions using the product, quotient, or power rules, the bases of all the logarithms in the expression must be the same. There are no rules on how to break up the logarithm of the sum or difference of two terms like this. The logarithm of m plus n to the base b is not equal to the logarithm of m to the base b plus the logarithm of n to the base b. And the logarithm of m minus n to the base b is not equal to the logarithm of m to the base b minus the logarithm of n to the base b. For example number 1, expand the given logarithms. Now, this is our given. The logarithm of 5y to the base 6 can be written to the logarithm of 5 to the base 6 plus the logarithm of y to the base 6. Another one, the logarithm of 10x to the base 8 can be written in the form of logarithm of 10 to the base 8 plus the logarithm of x to the base 8. Example number 2. Condense the given logarithms. If we have the logarithm of 8 to the base 3 plus the logarithm of x to the base 3, okay, it must be the logarithm of 8x to the base 3. Another one, the logarithm of 10 to the base 3 plus the logarithm of x to the base 2. We cannot use the product rule to simplify the given since the bases are different. Please take note for that. For example number 3, expand the given logarithm. The logarithm of a over 2 to the base 7. So we will use the quotient rule here. It is equal to the logarithm of a to the base 7 minus the logarithm of 2 to the base 7. Another one, the logarithm of 3 over x to the base 5 is equal to the logarithm of 3 to the base 5 minus the logarithm of x to the base 5. For example number 4, condense the given logarithms. If we have the logarithm of x cubed to the base 4 minus the logarithm of y to the base 4, it can be written as the logarithm of x cubed over y to the base 4. The logarithm of x cubed to the base 4 minus the logarithm of y to the base 2, we cannot use the quotient rule here to simplify the given because the bases are different. For example number 5, expand the given logarithm. The logarithm of x cubed to the base 2 is equal to 3 times the logarithm of x to the base 2, or this form. For example number 6, condense the given logarithm. 4 times the logarithm of 2 to the base 5 equals the logarithm of 2 raised to 4 to the base 5, or the logarithm of 16 to the base 5. So, we will be evaluating the logarithmic expression using its properties. For example number 1, expand the given logarithm and simplify in order to get the value of the logarithms. Now, here is the given. The logarithm of 4 cubed times 2 times 1 to the base 2. Now, we are going to use the product rule and our expression will become like this. The logarithm of 4 cubed to the base 2 plus the logarithm of 2 to the base 2 plus the logarithm of 1 to the base 2. After that, we have to consider first this first term, since it can be simplified using the power rule. So, it will become 3 times the logarithm of 4 to the base 2, and then copy the rest part of our expression. After that, 4 can be written into its exponential form, which is 2 raised to 2. So, it will become like this. 3 times the logarithm of 2 raised to 2 to the base 2. And still, we will be using the power rule. So, in using the power rule, it can be like this. 2 times 3 to the times the logarithm of 2 to the base 2. Okay? And this one, the logarithm of 2 to the base 2, it is equal to 1 because this is according to the second property of the logarithm. And the logarithm of 1 to the base 2, it is equal to 0. And that is according to the first property of the logarithm in the first set. So we are going to simplify them further. 2 times 3, the answer is 6. And then the logarithm of 2 to the base 2, the answer is 1 plus 1. And 6 times 1, the answer is 6 plus 1 is 7. So this is now our final answer. For example number 2, expand the given logarithm and simplify in order to get the value of the logarithms. Now here is the given. The logarithm of 32 to the base 2 minus the logarithm of 9 to the base 3 plus the logarithm of 1 to the base 4. Now here are the solutions. Copy first our given, and after which, okay, we are going to make this 32 into exponential form. And then transform also this 9 to its exponential form. And we have 3 squared and we have 2 raised to 5. And then you copy the third term. After that, we will be using the power rule for the first and the second terms because it shows exponent here. And then our equation will become 5 times the logarithm of 2 to the base 2 minus, okay, 2 times the logarithm of 3 to the base 3 plus the logarithm of 1 to the base 4. After that, okay, we are going to simplify them further by, okay, copy 5 and then times the logarithm of 2 to the base 2 is equal to 1 minus, okay, copy 2, the logarithm of 3 to the base 3 is equal to 1, and then copy plus the logarithm of 1 to the base 4 is equal to 0. And then simplify them further. 5 times 1, the answer is 5. 2 times 1, the answer is 2. So we have 5 minus 2 is equal to 3 as our final answer. Okay, so this time we will be proceeding on the logarithmic equation. So a logarithmic equation is an equation that involves the logarithm of an expression containing a variable. Solving a logarithmic equation can be done by rewriting the equation in exponential form and solve for the variable, applying the property of equality for logarithmic equations, or using the properties of logarithm. Okay, solve the logarithmic equation using the concept of exponential equation. So we have the logarithm of 81 to the base 3 equals x. Here are the solution. First, copy this given. After that, we are going to transform this logarithmic form into exponential form. So it will become 3 raised to x is equal to 81. Now, we are going to make this 81 into exponential form. So it will become 3 raised to 4. Why 3 raised to 4? Because when you are going to multiply 3 by itself in 4 times, the answer is 81. So our equation becomes 3 raised to x is equal to 3 raised to 4. Since the bases are the same, then we are going to apply the property of equality of the exponential equation. So therefore, we have x is equal to 4 as our answer, or the solution set is considered as 4. So the property of equality for logarithmic equation, let b be a positive real number and b is not equal to 0. Then the logarithm of m to the base b is equal to the logarithm of n to the base b, if and only if m is equal to n. For example number 2, solve the logarithmic equation using the property of equality for logarithmic equations. So here is the given. The logarithm of x squared to the base 2 is equal to the logarithm of 4x minus 4 to the base 2. Now, again, we are going to use the property of equality for logarithmic equation because the bases here are said to be the same. So if the bases are said to be the same, then x squared and 4x minus 2 should be equated. So our equation will become x squared is equal to 4x minus 4. And then transpose this 4x minus 4 to the other side of the equation, and it will become x squared minus 4x plus 4. Since this one is considered as a quadratic trinomial, we can factor this one out. So the factors are x minus 2 times the x minus 2 equals 0. After that, we are going to equate each factor with 0. So x minus 2 is equal to 0 and x minus 2 is equal to 0. Then get the roots and x is equal to 2. X is equal to 2 as well. Thus, the solution set is considered as 2, which is the multiplicity of 2. When we say multiplicity of 2, the number of times a given factor appears in the factored form of the equation of a polynomial is called the multiplicity. The zero or root associated with this factor, x is equal to 2, has multiplicity 2 because the factor x minus 2 occurs twice. For example, number 3, we need to solve the logarithmic equation. Okay? And here are the solutions. First, we are going to copy the given logarithmic equations. After that, since we look for the value of x and the first term consists of the variable x, we are going to transpose our second term to the other side of the equation. And it will become the logarithm of 4x to the base 2 equals the logarithm of 72 to the base 2 minus the logarithm of 9 to the base 2. Now, this right side of the equation shows the difference of the two logarithms. So, we are going to use the quotient rule. So, in using the quotient rule, our equation will become the logarithm of 4x to the base 2 equals the logarithm of 72 divided by 9 to the base 2. Simplify the 72 divided by 9 and the answer would be the logarithm of 4x to the base 2 equals the logarithm of 8 to the base 2. Since we have one term here and we have also one term here in both sides of our equations, okay, the bases also are said to be the same. Now, we are now going to use the property of equality of the logarithmic equations. So, we will be getting 4x and 8. So, equate this 4x and 8 and it will become 4x is equal to 8. Now, divide it by 4 both sides of the equation and x is equal to 2. Thus, the solution set is 2. For example, number 4, solve the equation involving natural logarithm. Why there is an involvement of natural logarithm? Because of this base e. So we are going to find the value of x. So here are the solutions. First, copy the given and then take the natural logarithm of both sides. And then after that, we are going to apply the power rule because of this exponent, and it will become x minus 1 or the quantity of x minus 1 times the natural logarithm of e equals the natural logarithm of 27. Now, evaluate ln e or the natural logarithm of e, which is equal to 1. So 1 times x minus 1 is equal to x minus 1, and then copy equals the natural logarithm of 27. After that, we are going to transpose this 1 to the other side of the equation, and it will become x is equal to the natural logarithm of 27 plus 1. Now, using your calculator, we are going to evaluate this natural logarithm of 27, and the answer is 3.295 836,866. Copy plus 1. and then combine using the addition process, and x is equal to 4.295836866, and our answer or the solution set is 4.2958. For example number 5, solve the given logarithmic equation. Now here is the given and the solutions as well. First, copy the given, and then since our left side of our equation shows the sum of the two logarithms which has the same bases, so we can apply the product rule here. So in applying the product rule, our equation will become the logarithm of 2x minus 1 times the 2x plus 1 to the base 5 equals 2. After that, we are going to make this equation into exponential form, and it will become 5 squared is equal to 2x minus 1 times 2x plus 1. After that, okay, get its product, and our equation becomes 5 squared is equal to 4x squared minus 1. After that, okay, simplify them further. 5 squared is equal to 25, and then copy the rest of the equation. And then transpose 4x squared to the other side of the equation, and it will become negative 4x squared, and then transpose 25 to the other side of the equation, and it will become negative 25 minus 1. So simplify them further, and it will become negative 4x squared is equal to negative 26. Divide negative 4 both sides of the equation, and x squared is equal to 26 over 4. To get the value of x, we are going to use the square root property of equality. So you are going to square root both sides of the equation, and this equation can be written into this form. And x is equal to positive and negative square root of 26 over square root of 4. Simplify them further. X is equal to positive and negative square root of 26 over the square root of 4 is equal to 2. And this is our answer. So the solution set is x is equal to square root of 26 over 2. Note, we reject the negative square root of 26 over 2 since it is not part of the domain. The domain of logarithmic function is x such that x is greater than 0.
Thank you for listening, math learners.